Here comes the sky.
Write the general equation for the position of an object in simple harmonic motion as a function of time. We can do that. X equals A sine omega times t. A is amplitude. X is position. Amplitude. Omega is our angular frequency. And then t is time. Remember that this equation can also be written as x equals a sine 2 pi f times t, because omega equals 2 pi over t. Omega also would then be 2 pi f, because frequency is the inverse of our period. So taking this, plugging it in there, we get 2 pi f. Suppose the vibrating object can be described by the position time function x equals 0.2 sine 7.31 times t, where x is in meters and t is in seconds. So this thing looks kind of freaky, right? But remember, this is just our amplitude. That 0.32 is our amplitude. Sine is the type of graph that it's going to be, and the 7.31 is omega. So just a word about this sine function. So the sine makes the graph start at 0 and go towards positive numbers. So that's what we're looking at here, a sine function. What the amplitude does is it tells me it's going to go all the way up to 0.32, I think was the number. If it's not, sorry. And then what the angular frequency is, the frequency is how often a cycle happens. So it's the condensing of these curves. Is it going to be wide like this, or is it going to have a tighter frequency? So the wavelengths are shorter. Really bad demonstration there, sorry. So the frequency is this, because remember, angular frequency equals 2 pi over t, or angular velocity equals 2 pi times our frequency, which is how often something happens. And if this goes all the way, that means we've gone 2 pi. Anyway, back to the problem. So